Welcome everyone. So this is our 81st live stream geometry session. We have two other people here with us right now. One of them is new. Simon is from Slovakia. And today I'm going to go over problems that I took from the user Live to Love 212 on Art of Problem Solving forum. So I think most of the problems I'm doing have been posted by him or her, but some of the other problems were posted by other people, and then he or she replied to them. So if you would like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to start sharing my screen. Okay, so here's the first problem. We have a triangle ABC with altitude AB, and G is the midpoint of AB. All right, so this is AB. Let me hide it. And G is the midpoint. I have to rename it. X is on GC and Y is on GB. So that, let's see, DX is perpendicular. Okay, so basically we drop the perpendiculars from B to those two segments. So dx, whoops, didn't mean to do that. Dx is perpendicular to GC, and dy is perpendicular to GB. So obviously this is a cyclic quadrilateral. And bx intersects cy at z. So this is x, and this is y. Hide those so that we just see the segment. So we have this, and then bx intersects cy at z. So let's make this look a little nicer. So that's point Z right there. And we want to show that the circle of XYZ and the circle with diameter AB are tangent. So let's draw those. This reminds me a lot of another problem we did recently. Oops. So we want to show that these circles are tangent. This looks kind of tricky. So yeah, maybe there's something special about the point of tangent C. Maybe it's collinear with D and Z. That looks like it might be true. Yes. Okay. So yeah, this looks really similar to another problem we did. I can't remember. Yeah, I'll have to go look at it after the session, but we used like Brocard's theorem. It was like a pretty kind of deep solution. So I don't know if we want to let DZ, what we could do is let DZ intersect the circle at E, and then try to prove that EYZX is cyclic. And then after that, we'd have to show it's also tangent. Or we could do it the other way. We could draw the circumcircle of XYZ. So yeah, I'm not sure which one is better. I'll leave it like this for now. So yeah, maybe we can use like Brocard's theorem. Maybe we could use inversion. I'm not sure. All right, it looks like Constantinitis is joining. Hey, Constantinitis. Thanks for joining us. Oh no, I think his connection must have been lost. He's rejoining. Hello. So yeah, this is the first problem that we just got started on. And it looks a lot like a problem recently on the channel. So what are some ways to prove it's cyclic? Power of a point. I wonder, let me draw both circles just to see. Is there anything special about this circle? Maybe let XY meet BC at a point. Let's try that. So if XY meets BC, I wonder if this is tangent to both circles, EF. So let's draw the tangent to both circles at E, because often that's a good way to show things. Yep, I just guessed it. See, isn't that a good guess? So it looks like EF is tangent to both circles. Okay, that's good information to know. Good thing I have GeoGebra and I'm not doing it with paper and pencil. Although in a competition, I couldn't do that. So, what here can I prove?
Intersect XY with ED.
With ED, okay.
Then we would have some harmonic bundles with that point H, I think, like because of these tangencies. So
okay, because this DE is the polar of F, and DZHE would have to be harmonic. Well, actually, I'm not so sure about that because XY is not the polar of D. But I think FYHX is harmonic. Yeah. So that's pretty helpful. Oh, no, not FYHX. I'd have to intersect this with the big circle. Sorry.
But it is actually.
Oh, really?
No, actually not. Yeah.
Okay.
May I ask you, what does it mean to be some points harmonic?
So before you can kind of say what harmonic is, you have to first define the cross ratio. So I'll do that in just a second. So Constantinitis said, so if I let P and Q be those points, then I would have something harmonic. So one sec. I'll explain in just a second.
Mm-hmm.
So yeah, I'm not sure if how helpful points P and Q will be, but F, P, H, and Q are harmonic. So like in this case, that would mean that PH over HQ is equal to FP over FQ. That means that F, P, H, and Q are in harmonic conjugation. So I'll say it one more time. PH over HQ is FP over FQ.
Okay, I understand. And how can it be helpful?
Yeah, so it's the proof of that is a little bit, there's a lot of stuff that actually goes into that. So I won't prove it all right now, but I actually did a video on my channel. If you look through the videos on my channel, there's like 2 on projective geometry, and then there's 2 videos on poles and polars. So if you watch those videos, it kind of explains how to do it.
Okay, I will do.
All right. BP intersects CQ. Okay. Is there something special about that point? Maybe A, I, and X are collinear. But yeah, so here's an interesting theorem about, and yeah, so I proved this in those videos, but I'll just show it really quickly. Let's say you have something like this in a triangle, and you have like 3 different like Chebians that concur. Then let's see. One sec, I'll check the chat in just a second, but I just wanted to show this. If you have something like this, so L doesn't have to be the foot of the altitude, L can be any point. But whenever you have a configuration like this, then these 4 points, R, J, L, and K are in harmonic conjugation. So yeah, it's just an interesting theorem. So JL over LK is RJ over RK. But yeah, you can, if you look through the videos, you can see the proof of that. All right, so let's check the chat. Power of a point at F. Yeah, so I think that's kind of a strategy. So if I hide this circle, well, I'll just keep it there for now, but yeah, we have to prove that this is tangent to both. So can we show that Fy times Fx is Fb squared? Because we want to show that's Fe squared, which is Fb squared. So that basically means that if we draw the circumcircle, oh, so we know this is cyclic, right? I said this in the beginning, but I forgot to draw it. So we know gy dx is cyclic. So we know Fb squared equals Fy times Fx.
Also, by power of a point at the G, BYXC is cyclic.
Interesting. Okay. So this is also cyclic. So that gives us a lot of information. Because then we know FB times FC is FD squared. So then that would mean that if we drew the circumcircle of EBC, that it would also be tangent. This would be tangent to all of them. So yeah, we have a lot of information here.
Could you please explain one more time why B, X, C, and Y are?
Yeah. So we have, since this is a right triangle right here, and DY is perpendicular, it turns out that GY times GB is GD squared.
Mm-hmm.
And then we also have GX times GC is GB squared. So that follows by similar triangles, because like whenever you have this right triangle and then here you drop a perpendicular, you have like 3 different similar right triangles. So you have like GB over GY is GB over GB. And so that's the same as saying basically GY times GB is GD squared. And GX times GC is GD squared. So since GY times GB equals GX times GC, by power of a point, those are cyclic.
Okay, I understood. Thank you.
Definitely. And I wonder if this passes through the center of that circle. So it's going to be a little bit hard to draw, but let me just check if it's true. Because then we might be able to use like Brocard's theorem or something like that. Yeah. Okay. I get really lucky with my guessing, right? So it looks like that passes through the center of the circle.
Take the midpoint of ED.
Okay. It looks like that lies on that circle.
Also, it should lie on circle BGC, but that is equivalent to showing that I lies on ED.
Okay. We want to show that I lies on the polar of F. So that's the same as saying F lies on the polar of I with respect to this circle. It almost looks like P and Q lie on A, B, and AC, but that's not true. I'm going to hide P and Q just for a second. Yeah, this is looking very similar to a problem we did recently. I forgot the solution to it. Yeah. You know what? I think this might be a special case of that problem. I think it was.
I think inversion around BYXC is really good, since what I haven't proved any of this, but it looks like AED stays the same and XYZ inverts to XYD.
Okay.
If we could prove those 2 claims, we would be done, since they are obviously tangent at D. XYD and AED are tangent at D.
Okay, so you want to invert around this circle,
Yeah.
and okay. And we want to show that this circle inverts to this circle.
And that AED stays the same.
Okay. So yeah, X and Y obviously stay fixed under that inversion, but do Z and E, we want to show they get swapped.
Z and J get swapped.
Oh, Z and J. Yeah, I was gonna say like IZ times IE seems a lot bigger than the radius squared. Okay.
But D and E get swapped.
D and E get swapped. So G is the midpoint of AB and J is the midpoint of EB. So yeah, it depends. I guess we should probably define E like that, right? And then try to show that this is cyclic. So yeah, can we show that FE is tangent to this circle? I think that would be a good first step because we know that I'm sorry, go ahead.
That is equivalent to showing I lies on ED.
Okay. Is that by Brocard's theorem?
I'm not sure how to prove it.
Okay. Well, so by Brocard's theorem, we know that IZ is perpendicular to FG, right? And then we know that DZ is perpendicular to FG. So does that kind of solve it?
How do we know that DZ is perpendicular to FG?
So I guess J.
It depends on how we define J.
Yeah. Are A, E, B, C cyclic? No. Define AD intersect that circle at K and L. Okay. Um, okay, I'm just going to assume L is down there. Then F, K, and L. Oh, do you mean KL is the polar of F? Or what do you mean by FKL? Oh, this circle. Sorry, I thought you meant the line AD. Yes, I see what you're saying. So, yeah, F lies on the radical axis of these two circles. And it looks like Z also lies on that.
I have found that it is actually not hard to prove that AD, ADE, that circle stays the same under the inversion.
Okay.
Because we want to show that that circle and the BYXC are orthogonal. But that is actually obvious because GD square is equal to GY times GB.
Okay, so we want to show that this is orthogonal to this, is what you're saying, right?
Yeah.
But GD squared is GY times GB, which is the power of G with respect to this circle. Okay.
So we would have like the tangents, GK
Yeah.
tangent, and yeah.
Okay. So this
That
circle
also proves that Z lies on KL because of the Brocard theorem.
Okay. So yeah, I think we're very close here. Yes. So if it's true that I lies on VE, yeah, I'm getting a little confused what we know and what we have to prove. But if I lies on VE, then I lies on the polar of F. So F would have to lie on the polar of I. So yeah, KL would be the polar of I. Okay. And that's basically the same as showing DZ is perpendicular to FG. So I'm going to hide this circle just well. Yeah, how do we know DZ is perpendicular to FG?
Oh, I think I proved that Z, D, and I are collinear.
Okay.
So we'll use poles and polars. I
Okay.
have already proved that ADE and BYXC are orthogonal.
Mhm.
And so we see that IK and IL are tangents from I to that circle.
Okay.
So by Broca's theorem, we have already showed that FL, Z, and K are collinear, I think.
Okay. Yeah, I'll have to write this all out just to remember, but okay, let's assume that's true.
So because I think that is true because it is the polar of G with respect to BYXC.
Okay.
So because like K and L are the tangents, so GK and JL are tangents. And by Broca's theorem, Z lies on the FZ is actually the polar. So all of those lie on a line.
Okay.
And so because LK is actually the polar of I, then and F lies on it, then I lies on the polar of F.
Right. So ED and I are collinear.
I think we should not
Assume
do
that this
anything.
is tangent. Yeah, no, I agree.
Yeah,
So
yeah,
I lies on the polar BF. Yeah.
yeah. Also, obviously, D lies on the polar of F. So DI is the polar. And again, by Broca's theorem, it is Z lies on the polar of F with respect to BYXC. But yeah, just like he wrote in the chat.
Okay.
It's harmonic. So I think we're done because that was actually the only thing we needed to prove.
All right.
Basically.
Do I need point J or let me
I think we will need it just for because it is the Mikkel point of BYXC. So to state the inversion correctly, like I think we will.
Okay. So
Basically, because we know now that Z, D, and I are collinear, it is well known that Z inverts to J if we define J as the Mikkel point of BYXC.
okay. All right. So yeah, I think there's probably a way without inversion, right? I guess inversion, but we can still try it. So let's see. All right, so let's do this step by step. So first I'll start out by saying let X, Y intersect BCF. And then let BZ, yeah, it's all a matter of how we want to define things, right?
Okay. J we should define as the Mikkel point of BYXC.
Okay. So let J be the Mikkel point of BYXC. So first we're going to show BYXC is cyclic. So we have GY times GB is equal to GB squared, which is equal to GX times GC. And that means that BYXC is cyclic. Let BYXC intersect the circle with diameter AD at K and L. Okay. This should be Mikkel. Okay, so then the Mikkel point, basically that means FBYJ is cyclic. It's the intersection of all those circles, right? Oops, sorry. Not going to draw that circle, but orthogonality now. Okay, so then we have GD squared equals GY times GB. That means that those two circles are orthogonal because so basically GD would be the length of the tangent to this circle. Okay, and that would be GI squared minus the radius squared. So since GD squared equals GY times GB, that means that BYXC is orthogonal to the circle with diameter AB. Okay. So basically this implies that I, Z, and J are collinear, right? By a well-known fact. So once J is the Mikkel point of BYXC, then we know that I, Z, and J are collinear, right? Then we have this. So Z, we want to show Z has the same power with respect to these two circles. So by Brocard's theorem, IZ is the polar of F. So basically this means IZJ and D are collinear. I'll say since D clearly lies on the polar of F.
I think you should be careful about which circle you're talking about when you say polar.
Okay. I agree. So this, yeah.
If those 4 points are collinear, that is the key part of the problem.
Okay. So the polar of F. Yeah, no, actually, I think I got confused a little bit. So GF so IZ let me use this tool. GZ is the polar of F. I don't know, I kept thinking, I got confused a little bit. Okay. So IZ and J are collinear. So that I think that's the well-known fact, right? That IZ and J are collinear, but not B. Is that true?
Yeah.
Yeah. Okay. Okay, so what is the next step here?
I think you should say Y, F, L, Z, and K are collinear.
Okay.
And that is because those four make the polar of G with respect to BYXC.
Okay, so this means that K and L are on the polar of G. Because yeah, GL squared. Okay, so K and L lie on the polar of G, and then by Brocard's theorem, F and Z lie on the polar of G, right? On the polar of G with respect to BXYC or BYXC. And then by Brocard's theorem, F and Z is the polar of G. C, and that means that F, Z, K, and L are collinear. Here. So I'll put that down here. And then
we can one by one say why Z, D, and I lie on the polar of F with respect to ADE.
Okay.
So for example, for D, it is quite obvious, just FD is the tangent.
Yeah.
For I, we have that IL and IK are tangents because we have that
Orthogonal.
circles. Yeah. And Lahira's theorem then finishes that. And for Z, we can just say because FZL and K, they are in harmonic conjugation since because of the previous polars here.
Okay. Yeah. So
is that true? I mean, it is true, but is it something we can state?
well, we only know they're in harmonic conjugation if we know. So ID, so D is on the polar of F with respect to this circle. I is on it because these are tangents. So since F is on the polar of I is on the polar of F. But yeah, for Z, I'm trying to think about Z. So we said that if these are in harmonic conjugation, then that's true. But so yeah, the question is, how do we know Z is on the polar of F with respect to this circle? So
That is just Brocard's theorem.
okay. Yes. So since Z is on the polar of F, hey Yash, thanks for joining. Okay, so Z, okay, so sorry, I'm gonna move this out of the way. Okay, so
Yeah, it just follows from Brocard's theorem.
So Z is on the polar of F with respect to this. So so then that means Z also has to be on the polar of F with respect to this, basically. So that's interesting. So basically we're saying since Z, yeah, and it's not, you know, hard to show, but basically we're saying since Z is on the polar of F with respect to this circle, it's also on the polar of F with respect to this circle. Because since one's in harmonic conjugation, the other is also, right? That kind of makes sense.
Yeah, that's true.
Okay. So Z is on the polar of F with respect to BYXC. That means that FKLZ is in harmonic conjugation, or I'll say LK. And that implies that Z is on the polar of F with respect to the circle 8B. The circle with diameter 8B. And that means that Z, D, and I are collinear. So we know D lies on it and I lies on the polar by Brocard's theorem. So by Brocard's theorem, see, I'll add that. Polar of F. BYXC. Okay, so I think this does it basically. Because we know I lies on the polar of F, we know D lies on it. Wait. Yeah, now I'm getting confused. Oh, because I is also the center of this one. Yeah, okay. So really we should switch these two around. So we're kind of, yeah. ZDI are collinear. And yeah, this is a little, I'm gonna break this up into another line. That looks better. Okay, so we know ZD and I are collinear. I'll say ZDI and J. I'll say let this line meet AD at E. That circle at E. And then
I don't think we even need this point. E.
Okay.
Since we just state the inversion and then we're done.
Okay. All right. Yeah, I agree. And then, okay, an inversion about BYXC fixes that circle and swaps dx dy and xyz, and that implies AD is tangent to xyz. So I think that should do it. There is a lot that went into this. All right, let's see what time it is. It's almost 10, so yeah, I'm gonna move on to the next one in just a second, but I just wanna make this look a little nicer. Yeah, sometimes on YouTube, if something's at like the very bottom, you can't see it that well. So I'm gonna move this stuff up. So this circle's fixed because it's orthogonal to the XYC. And these circles are swapped because, so X and Y are obviously fixed, but once we know that these are all collinear, then we know that J and Z are swapped. Okay, I'm just gonna leave it at this for now, just because I want to move on to the next one, but that is the idea. All right, so here's a problem from Germany's team selection test. You have a triangle ABC, H is the orthocenter and O is the circumcenter. So we have AP is perpendicular to BC. So yeah, I'll let D be the foot of the altitude, and P is kind of just any point on this. And Q and R are the reflections of P and CA and CB. All right, so it's probably worth drawing a few other points then. So this is Q, and this is R. And yeah, I'm going to draw these points here just because I think they might be useful. And is it true that RA and Q are collinear? I think it's true. No, it's not true. Okay. Just trying to draw a good picture. Okay, so obviously these are, so A is the circumcenter of RPQ because AR is AP equals AQ, right? So I'm gonna draw these just for the heck of it. So A is going to be the circumcenter of this. Okay. Y is the projection of R onto CA. And then, okay, so what does that look like? Okay, I'm gonna want to make this diagram look a little better. So we have a Y and a Z. Let's see, how do I make this look better? If, I don't know if making it, Yeah, I don't think I can make them both on the sides A, B, and AC. I don't know if that's possible, right? Oh, maybe it is. If I make it like a really tall triangle, there we go. Okay. So that looks pretty decent. I'll make it like a little taller. There we go. All right, so let me shrink it just a tiny bit. So this is Y, and this is Z. And we're going to want to draw, I still haven't drawn the orthocenter and the circumcenter. Do that in just a second. Whoops. But yeah, Simon, that last question required a lot of like theory about projective geometry. So yeah, maybe this problem won't use as much theory, but yeah, there was a lot of like stuff that, yeah, you'd probably have to research a little bit first. But yeah, if you're speaking, you're on mute. But yeah, I just want to mention it. Okay, so this is O. Let me make it look like it doesn't lie on PE. There we go. And then I draw the orthocenter H. Okay. We want to show YZ is perpendicular to HO. Looks like a tricky problem. So yeah, basically, I think we can really make P wherever we want, I think, because it would just be a homothety about A. Well, yeah, I think so, right? Like this whole figure is homothetic wherever we put point P, right? So we could assume P is point H if we wanted. Or point D. What do you think? You want to just assume P is point H?
H looks the best.
Yeah, I agree.
Can we do that? Shouldn't we go like a more general case where these 2 points aren't congruent?
Wait, say one more time. Oh, yeah, we can reduce the problem to the case where P is equal to point H. And the reason why we can do that is because basically as I move point P along segment AB, if you look at this whole figure right here, AR, PQ, and then AF and AE and YZ, it's just like a scaling of the same figure, right? So it stays, all these points stay the same shape, but they just get scaled. And so basically YZ is just keeps being parallel to the same, wherever Y and Z move to, they're always parallel to where they were before. And so if we want to show YZ is perpendicular to OH, we can just assume P is really any point we want. And so we can assume P is point H, if that makes sense.
I figured this, since there is no restriction in the problem.
Yeah, so the problem says there's no restriction, but basically I'm basically proving that even though the problem says there's no restriction on P, if we can prove it when P is equal to H, that will in turn then that will help prove it when P is a different point. So Yeah. Choose P, the reflection of H. Oh, that works better. Interesting. All right, let's see. So if P is the reflection, if P is this point right here, so yeah, I'm not sure which is better, but really we want to show that we could try to show that YH squared minus ZH squared is YO squared minus ZO squared. Simpson. So yeah, so then we could use the Simpson line. And that would show that R, H, and Q are collinear. Because basically by the Simpson line, we know that G, D, and E are collinear. And so that means that R, H, and Q are collinear. Because they're each reflections of P. So yeah, we could also do that. One sec, I'll be right back. All right. Okay, so like for YO squared and ZO squared, if we take the difference between their powers, so it'd be like AZ times ZB minus AY times YC. That would be YO squared minus ZO squared. And then can we find YH squared minus ZH squared? I wonder, what if, what point would make it easier to calculate YH squared and ZH squared? So let's see, if we set P equal to H, then yeah, so we have a couple different choices. Yeah, this or this. Whichever one makes it easiest to figure out YH squared minus CH squared. So I wonder, does it ever happen where HY equals HC? I don't think that's possible. So here's a really weird idea that I just had. It's kind of interesting. Let's say we draw like this triangle where the sides are like double ABC and parallel. Then H is the center, H is the circumcenter of this triangle. And so the power, oh, actually that wouldn't work too well. I wanted to try to find the power of Y and Z with respect to that circle, but I think that just makes it harder. Okay, never mind. What if we move? Yeah, I want to be able to find HZ. So yeah, is it ever, how do we find ZH squared? Is there some right triangles we can use? You know, this is a right triangle. Is there some kind of good circle through H that we can use? I don't know. I don't think so. Yeah, I have to use the definition of Y and Z, and I feel like I kind of keep forgetting that. Let me go back to letting P equal H. So ZH squared, that's what we want to find. That's GH squared plus CG squared. Maybe this is bashable. because ZH squared, we could also say ZH is ZR, right, by symmetry. Is that always? Yeah, that's actually just true in general. So, well, if we let P equal H, then ZH is ZR and YH is YQ. So then we want to find ZR squared minus YQ squared. I don't know if it helps. Then ZR YQ.
But we can really bash this.
It should be bashable, right?
Yeah, because we can calculate the ZG.
Yeah, because ZG is just ZB times like QH over BH. Yeah, so I think this is bashable. So I'm going to try it right now. So I'll start out, I'll say first assume the case when P is equal to H, and then I'll show how the actual problem follows from it. So complex numbers were, you know, I don't like complex numbers on my channel, but in a competition, it's probably the best way to solve it. And I think that's how Buratino himself would probably solve it in a competition, because I've seen on art of problem solving forums for like the very hard problems, he just, uses complex numbers. So we'll say first consider the case where P equals H, and then we'll show how the general case follows from it. Okay, so we want, so first ZH squared minus YH squared. Let me check the chat. Oh yeah, complex numbers. That's ZG squared plus HG squared minus YE squared plus EH squared. And that, so ZG is, it's going to be basically BZ, or I'll say it's HQ. Yeah, what's the best way? It's BG times HQ over HB. And then HR over HC, and then minus HE squared. Okay. And HQ is just 2HE, and HR is 2HG. And then CE over HC, that's like, is that sine or cosine of A? Let's see. So CE, so this is angle A. So CE over HC, that's going to be sine A. So is equal to, so that's 2HQ, or wait, so HB, BG and HB. No, so this is 2HE sine A squared plus HG squared minus 2HG sine A squared minus HE squared. And then we use the double angle formula, or so this would be equal to 4 sine squared A minus 1 times HE squared minus HG squared. I think this is all right, although I'm not sure. And we want to show, okay, so that's ZH squared minus YZ squared. Then what about ZO squared minus YO squared? Well, that would be the difference in the powers, which would be AZ times ZB minus AY times YC. Which yeah, so yeah, basically we want to show ZO squared minus YO squared is equal to this, right? So what if I wonder if Z is the midpoint of this. Kind of looks like it. Is that true in general? Or if P is equal to H? So is this a right angle here? It kind of looks like it. And then if I did it like this, then would Y be the midpoint of this? It looks like it. Right? Actually, I wonder if this point is the orthocenter. Well, it is the orthocenter, actually. Okay. So basically, yeah. So that, I think that kind of helps solve it, because we draw this point and this point. I is going to be the orthocenter of ABQ. So when you reflect it over AB, it lies on the circle. And then basically, ZJ times ZQ, that's the same as ZQ times IZ. And then which is the same as A, so ZQ times IZ. Do you see a good way to bash this?
Well, you need the ratio of, difference of powers of z and y.
Yes.
You can like calculate ZA times ZB, right?
So ZA, so what I was thinking is ZA times ZB is the same as ZJ times ZQ, which is the same as ZI times ZQ. But I don't know if that helps.
You can probably just calculate ZB and that's it.
Just ZB. So ZB, oh, that's just BQ times this angle. Yeah, you're right. So yeah, I don't really need this, because we know that this angle is 90 minus A. So, and then BQ, yeah, okay. So actually, I still want to draw QZ. There you go. Okay, so first BZ is equal to BQ, because this angle's A. So BZ is BQ sine A. And make this look better in a second. So that, which, and BQ is BE plus EH. BE sine A. So BE sine A is AB, right? Wait, that doesn't make sense. So BE, so sine A is BE over AB. So BE sine A would be AB. That doesn't make sense. I think I'm doing something wrong here. So this step looks right. Then this seems right. So where did I go wrong? Oh, BE sine A is BE squared over AB. That's what I'm, so this is right. Yeah. Okay, so this, so BE, okay, so this is BZ, and then we also have CY. That would be CF, what is it? CF, CG plus GR. And then AB, AB is BE sine A. So actually, let me just rewrite the, oh no, it's AB is BE over sine A. And AC is CG over sine A. Let me just do it like this. So BZ times ZA is BZ times that's BZ times AB minus BZ, which is equal to BZ times AB minus BZ squared. And that is BE times BQ minus BQ squared over sine squared A. Let's see how this looks. Okay, so we have this expression, and then we have the same expression for Y. And then we want to show that when we subtract them, we get this. Seems like it, is there a faster way? So BQ and yeah, we know this is cyclic, right? BGEC. So QE times QB is the power of Q with respect to this. And RG times RC is the power of R with respect to this.
Could you please explain one more time how did you get the last two equations together in the last line?
Yeah, so
BZ times AB minus B is BZ squared is equal to B times BQ and the rest of it. Yes.
yeah, so basically I used these two formulas. So I have BZ is BQ sine A and AB is BE over sine A. And so when I multiply these two, the sine A cancels, and then I get BE times BQ.
Oh, right. Mm-hmm.
And then BZ squared, I use this.
Mm-hmm. Okay, I overlooked that. Okay, thank you.
Sorry?
I said that I overlooked that.
Oh, it's all right.
Can we also use the fact that H, with orthocenter and circumcenter are isogonal conjugates in a triangle?
Yeah, that's true. Yeah, H and O are isogonal conjugates.
So maybe that might help us.
Yeah.
Since we already have the isosceles triangle ARH, and then, well, when we connect A and O, we will get another an angle on the same value. So that might be helpful.
Okay, so yeah, ARH is isosceles, and yeah, we know angle GAH is angle EAO. So yeah, that could help. I feel like it might also help. So I haven't used that A is the circumcenter of this. All right, you want to come back to this problem later? see if we can finish up the calculation later.
Okay. May I ask you in the meantime, how did you also get the second line of the of those equations, the like zh squared minus yh squared, and then the second line? How did you get from the first one to the second one?
Oh yeah, so the first one is the Pythagorean theorem, right?
Mhm.
The second line, so basically I'm using, so triangle BGH is similar to triangle BZQ, because HG is perpendicular, like these two are both parallel, QZ and HG, because they're both like perpendicular to AB. So basically by similar triangles.
Oh, I see now. Okay.
Oh, okay.
Thanks.
Yeah, you're welcome. All right, so I'm going to move on to another problem and come back to this later. Oh, this one looks kind of hard. Let me see. This one I don't think is, yeah, this one looks interesting.